What if I told you there are places in our universe where a magnetic field is so powerful it could tear the very atoms of your body apart from 1,000 kilometers away? Picture that for a moment, a force so unimaginably intense that it doesn't just bend metal or redirect compasses, but warps the very fabric of space and time, twisting matter into forms we can barely comprehend. These aren't scenes from science fiction. They are real, violent, and breathtaking phenomena taking place right now in the darkest corners of our cosmos. And today, we're going to explore them together. Welcome, space enthusiasts and curious minds. Have you ever looked up at the night sky and wondered what truly lies beyond what our eyes can see? Beyond the gentle glow of stars and the serene beauty of galaxies, there exists a hidden universe of extreme forces, ones that challenge everything we think we know about physics, reality, and our place in the cosmos. Among the most mysterious and powerful of these forces are magnetic fields, but not like the ones you learned about in school. We're talking about magnetic fields with the power to crush neutron stars, warp spacetime, and generate energies that dwarf anything our sun could ever produce. In this video, we're diving deep into 30 incredible facts about the universe's most extreme magnetic fields. This isn't just a list of interesting tidbits. It's a journey to the edge of understanding, where the laws of physics as we know them begin to break down, and where nature reveals its most spectacular and terrifying secrets. From magnetars with magnetic fields a quadrillion times stronger than Earth's, to cosmic laboratories where matter is stretched and shredded in ways that sound more like magic than science, this is a story of extremes, of beauty, and of mystery. So settle in, open your mind, and get ready to explore the invisible forces that hold some of the greatest power in the universe. To even begin understanding these cosmic monsters, we first need to grasp the scale of their power. We often measure magnetic fields in a unit called Gauss. The Earth's magnetic field, the one that guides compass needles and protects us from solar radiation, is a relatively gentle 0.6 Gauss. A typical refrigerator magnet is about 100 Gauss. Now, hold on to that thought, because a magnetar's magnetic field is approximately 1 quadrillion Gauss. That's a 1 followed by 15 zeros. To say it's stronger is a galactic understatement. It exists on a completely different plane of reality. At just 1,000 kilometers away, a stone's throw in cosmic terms, such a field would be utterly lethal. It would not just erase the data on every credit card on Earth. It would literally warp the electron clouds of the atoms that make up your body, pulling and distorting matter at a subatomic level in a process called spaghettification. These behemoths aren't born from peaceful beginnings. Their creation is one of the most violent events in the universe. They start as a massive star, many times larger than our sun. When such a star finally exhausts its nuclear fuel, its own immense gravity causes it to collapse in on itself in a spectacular supernova explosion. What remains is an incredibly dense core, a neutron star where matter is packed so tightly that a single sugar cube-sized amount would weigh as much as a mountain. But for a select few of these neutron stars, the conditions are just right or perhaps just terrifyingly wrong for a magnetar to form. During that catastrophic collapse, the star's original magnetic field, along with its rapid rotation, gets concentrated and wound up tighter and tighter, like a cosmic spring coiling beyond its limit. This dynamo effect, happening in a sphere just 12 miles across, creates the most powerful magnetic fields known to science, and their effects are as bizarre as they are destructive. We're not talking about simply attracting metal. A magnetar's magnetic field is so intense that it can actually crack the star's own solid crust, which is harder than steel. These events, known as Starquakes, release titanic bursts of gamma rays and X-rays. In a matter of seconds, a single starquake can unleash more energy than our sun will emit over 100,000 years. This isn't a gentle flicker, it's a universe-altering shudder. In 2004, radiation from a starquake on a magnetar 50,000 light-years away actually compressed Earth's upper atmosphere and briefly disrupted radio communications worldwide. From halfway across the galaxy, this remnant of a dead star reached out and touched our planet, a stunning demonstration that in the cosmos, even the most distant and invisible forces can have a very real and tangible impact. To truly appreciate that staggering figure of 1 quadrillion Gauss, let's bring it back home for a moment. Our own planet generates a magnetic field, a gentle but vital force that shields us from the sun's harmful radiation and guides migratory animals across the globe. This protective bubble, which is absolutely essential for life as we know it, measures a modest 0.6 Gauss. A simple magnet you might stick to your refrigerator is about 100 times stronger than that. Now try to envision the leap from that humble fridge magnet to the most powerful human-made magnetic fields, like those inside a cutting-edge MRI machine used for medical imaging, which can reach around 100,000 Gauss. That machine represents one of the most intense concentrated magnetic forces we can create with our current technology. Now, take that immense power and multiply it not by 1,000 or even 1,000,000, but by 10 billion. You are now beginning to approach the incomprehensible strength of a magnetar. This isn't just a difference in degree, it's a difference in kind. The magnetic field of a magnetar operates on a scale where the normal rules of physics and matter no longer apply in any recognizable way. It transforms the space around it into a laboratory of extreme phenomena, where particles are forced into bizarre shapes and light itself is twisted and bent in impossible directions. This comparison isn't just about numbers on a page. It's about understanding that within our universe, there exist forces so far beyond our everyday experience that they might as well be magic, yet they are undeniably, terrifyingly real. But that unimaginable power isn't static, it's actually fading, and its slow death throes are what create some of the most violent events we can observe. These magnetic fields are so intense that they simply cannot be maintained forever. Over thousands of years, they gradually decay, and as they do, they release absolutely colossal amounts of pent-up energy. This isn't a gentle, quiet fading. It's more like a massive dam developing countless tiny cracks, each one releasing a torrent of energy that has to go somewhere. That somewhere is directly into the star itself. The crust of a neutron star is a perfect place for this energy to manifest its fury. This isn't a soft, gaseous surface like our sun's. It's a shell of material harder than any diamond or steel we could ever conceive of on Earth, crushed into a crystalline lattice by the immense gravity. Yet, even this ultra-rigid structure is no match for the stresses of a decaying magnetic field. The energy building up from the decay creates immense strain, warping and bending this super-dense crust until finally it can take no more. It fractures. In an instant, the entire crust of the star adjusts, shifting in a cataclysmic event we call a starquake. The scale is almost impossible to overstate. This single crack on an object only about 12 miles across releases more energy than a magnitude 32 earthquake, a value so high it defies the scales we use for our own planet. And just like an earthquake, this sudden movement has a direct and observable effect. It changes the star's spin. Astronomers call these sudden changes glitches. We can detect them from Earth as a tiny but abrupt change in the incredibly rapid and precise rotation rate of a pulsar. One moment, its radio beacon is ticking with the regularity of the universe's most accurate clock. The next, the rhythm is broken. The star has suddenly, imperceptibly to the human eye, started spinning just a fraction of a second faster. That tiny hiccup in data, picked up by our most sensitive radio telescopes, is our direct evidence of a catastrophic geological event occurring tens of thousands of light years away, all powered by the slow and violent death of a magnetic field. While the slow decay of a magnetic field leads to the crust-shattering violence of a starquake, there exists an even more spectacular and instantaneous form of eruption, the giant flare. If a starquake is like a catastrophic earthquake, then a giant flare is the detonation of a magnetic bomb. This is not a slow release of pent-up stress, but a sudden, catastrophic explosion where the magnetar's entire magnetic structure momentarily tears itself apart. The trigger is a process known as magnetic reconnection, a concept we see on a much smaller and gentler scale on our own sun during solar flares. On a magnetar, however, this process is elevated to a literally astronomical level of fury. The star's magnetic field is under such unimaginable strain that the field lines, which are normally loops of immense energy, can become twisted and tangled beyond their breaking point. They snap. In a violent instant, these lines of force rupture and then explosively reconnect into a new, more stable configuration. But the energy that was stored in those distorted lines has to go somewhere, and it is released in a single, blinding flash of radiation so powerful it defies human comprehension. We are talking about an event where, in just a few tenths of a second, a single object can unleash more energy than our sun will radiate across the entire electromagnetic spectrum over 100,000 years. To put that timescale into perspective, 100,000 years ago, modern humans were just beginning to migrate out of Africa. The total energy our sun will output from that point until today is ejected by a magnetar in less time than it takes you to blink. The flash is so intensely bright in gamma rays and X-rays that it can temporarily outshine every other gamma ray source in the entire galaxy, including the combined light of every other star, nebula, and black hole. We have witnessed these events from Earth. On December 27, 2004, a magnetar 50,000 light-years away in the constellation Sagittarius produced a giant flare so powerful that, despite being halfway across the Milky Way, it actually compressed Earth's ionosphere and briefly disrupted long-range radio communications. It was the brightest event of its kind ever recorded from outside our solar system, and for a fraction of a second, this invisible remnant of a long-dead star became the brightest object ever seen in the sky by human instruments beyond our sun. It was a stunning and humbling reminder that the universe is capable of generating forces on a scale we are only just beginning to measure, and that even from a distance of 50,000 light-years, the death throes of a star can still reach out and touch us. This brings us to a specific moment in history, a day when a cosmic event became personal for our entire planet. On December 27, 2004, at 21 hours, 30 minutes, and 26 seconds universal time, a wave of energy that had been traveling through the void for 50,000 years finally reached Earth. Its source was a previously known object named SGR 180620, a magnetar located in the constellation of Sagittarius. In less than a fifth of a second, this object unleashed a giant flare of such immense power that it became, and still remains, the brightest event from outside our solar system ever recorded by human instruments. For that fleeting instant, this single point in the sky outshone the full moon in gamma rays, becoming brighter than any gamma ray burst we have ever observed. The flash was so intense that it actually saturated the detectors on nearly every spacecraft designed to watch for such events. Our most sensitive instruments were momentarily blinded by the sheer force of it. But the effects were far more tangible than just a bright reading on a sensor. That incredible blast of high-energy radiation shot across the galaxy and slammed directly into our planet's protective layers. When those X-rays and gamma rays hit Earth's ionosphere, the uppermost layer of our atmosphere, they did something extraordinary. They caused a sudden and massive ionization event. Essentially, the energy was so powerful that it ripped electrons away from their atoms, drastically and instantaneously changing the electrical properties of that region of the sky. The pulse was so strong that it caused a sudden, sharp compression of the ionosphere itself, a ripple in our protective bubble that was measurable from the ground. The practical effects were immediate and global. long-range radio communications, which rely on bouncing signals off the ionosphere to travel over the horizon, were significantly disrupted. Airline pilots on polar routes reported static and loss of signal. Satellites in low Earth orbit were bombarded with radiation. Some were temporarily disabled as their systems struggled to cope with the particle onslaught, and others were permanently damaged. What's truly staggering to consider is the distance involved. The magnetar SGR 180620 is not a nearby object. It sits 50,000 light-years away from us, meaning the light and energy that affected our world in 2004 had begun its journey during the last ice age, when Neanderthals still walked the Earth. For that energy to remain potent enough after traveling across half the Milky Way galaxy to still physically alter our atmosphere and disrupt our technology is a testament to an almost incomprehensible scale of power. It was a profound and humbling reminder that we are not isolated observers of the cosmos. We are participants living within a dynamic and sometimes violent universe where events occurring in the most distant reaches of space can, and do, reach out across the unimaginable void to touch our world in very real ways. So how do we even begin to study something we can't see? An invisible force field trillions of times stronger than anything on Earth that exists tens of thousands of light years away. The answer lies not in looking for the magnet itself, but in witnessing its incredible effects on the universe around it. We detect these invisible giants by observing the high-energy fireworks display they force into existence. Think of it like trying to study the wind. You can't see the wind itself, but you can see the leaves it rustles, the flags it waves, and the clouds it pushes across the sky. For a magnetar, the leaves are subatomic particles, and the wind is so strong it whips them into a frenzy of light. The primary way we spot these cosmic powerhouses is through their dramatic emissions of X-rays and gamma rays, the most energetic forms of light in the universe. This light isn't produced by the star's heat, it's generated directly by the magnetic field's unimaginable power. Here's how it works. The magnetar's surface is constantly shedding a fog of electrons and other particles. In the grip of a normal magnetic field, these particles might just drift away, but caught in a magnetar's quadrillion Gauss grip, they have no choice but to follow the magnetic field lines that arc high above the star's surface. These particles are accelerated to velocities approaching the speed of light, forced to spiral along these invisible paths. This violent, spiraling acceleration is a fundamental process in physics, and it causes the particles to scream out their energy in the form of high-energy photons, specifically X-rays and gamma rays. It's this persistent, powerful glow that allows our telescopes to pinpoint a magnetar's location, acting as a brilliant beacon signaling the presence of an immense hidden magnetic field. This is where some of humanity's most advanced eyes in the sky come into play. Space-based observatories like NASA's Fermi Gamma Ray Space Telescope and the Nuclear Spectroscopic Telescope Array, or NuSTAR, are specifically designed to see the universe in these high-energy wavelengths. They don't see the beautiful swirls of galaxies or the colorful clouds of nebulae in the same way the Hubble Space Telescope does. They see a universe of violent processes and extreme physics. Fermi is a master at detecting gamma rays, the telltale signature of the most energetic events. When a magnetar has a starquake or unleashes a giant flare, Fermi's detectors light up, recording the intensity and timing of these catastrophic bursts. NuSTAR, on the other hand, excels at focusing on high-energy X-rays, allowing it to create incredibly detailed images and spectra. It can stare at a magnetar and analyze the specific energy signature of the light being emitted by those spiraling particles, giving scientists precise data on the magnetic field's strength and structure. Together, these instruments don't just see a point of light. They translate the invisible dance of particles into data, allowing us to paint a detailed picture of forces that defy earthly imagination. Every flash and every flicker we detect is a direct message, a piece of the puzzle sent across the galaxy. helping us decode the mysteries of the universe's most extreme magnetic environments. But what cosmic engine could possibly generate such an inconceivable amount of magnetic power? The leading theory that scientists use to explain this incredible phenomenon is known as the alpha-omega dynamo. Imagine the chaotic moments following a supernova explosion as the core of a massive star collapses into a newborn neutron star. This sphere, only about 12 miles across, is a cauldron of unimaginable energy. Its interior is a bizarre soup of superfluid neutrons that can flow without any friction whatsoever, and it is spinning at a dizzying rate, completing multiple full rotations every single second. This combination of rapid spin and churning convective motion in the interior acts like the ultimate cosmic generator. It takes whatever tiny, pre-existing magnetic field the original star had and begins to stretch it, twist it, and wrap it around the star's axis of rotation. Think of it like spinning a ball of yarn, but instead of yarn, it's lines of magnetic force, and instead of a gentle spin, it's a vortex of unimaginable power. Every rotation tightens the coils, amplifying the magnetic field exponentially. In a matter of seconds or minutes, this dynamo effect can transform a relatively ordinary magnetic field into a magnetar strength monster. It's a perfect, terrifying storm of physics, the conservation of the star's original angular momentum forcing it to spin faster as it collapses, and the incredible turbulence in its newborn heart providing the motion needed to wind that magnetic spring tighter than anything else in the known universe. This isn't a slow process, it's a violent, explosive amplification that forges the most powerful magnets in the cosmos in the blink of a cosmic eye. While magnetars represent the absolute peak of magnetic power in the universe, it's crucial to understand that they are a very specific and rare breed of neutron star. Think of neutron stars as an entire family of incredibly dense stellar remnants, and magnetars are the extraordinary, hyper-powered outliers. All magnetars are neutron stars, born from the same violent supernova explosions, but the reverse is not true at all. The vast majority of neutron stars are what we call radio pulsars. These are still phenomenal objects, spinning at dizzying speeds and sweeping beams of radiation across the galaxy like cosmic lighthouses. But their magnetic fields, while still monstrous by any earthly standard, are orders of magnitude weaker. Where a magnetar's field measures around 10 to the 15th power Gauss, a typical pulsar operates at a mere 10 to the 12th power Gauss. That difference of a factor of 1,000 might not sound like much, but in the logarithmic world of astrophysics, it represents a fundamental chasm in behavior and capability. A pulsar's magnetic field is powerful enough to accelerate particles and generate its iconic lighthouse beam, but it lacks the transformative, reality-warping intensity that defines a magnetar. You would not get starquakes or giant flares from a standard pulsar. Its crust remains stable under the comparatively gentler magnetic forces. This distinction is not just academic. It's the key to understanding why some dead stars become these volatile, eruptive monsters, while most settle into a long, stable life as precise cosmic clocks. The difference lies in the conditions during their birth, the initial spin rate, the mass of the progenitor star, and the exact mechanics of the collapse that determine whether the internal dynamo gets wound up to magnetar levels or stops at the level of a normal, if still incredibly powerful, pulsar. It's the difference between a steady hum and a catastrophic explosion. This incredible power, however, comes with a cosmic expiration date. Unlike the relatively stable magnetic fields of planets or stars, the unimaginable strength of a magnetar is a fleeting phenomenon in astronomical terms. These objects are essentially the volatile teenagers of the neutron star world, bursting with incredible energy but destined to mellow with age. A magnetar's furious activity is a direct product of its youth, with most being perhaps only 10,000 years old. To put that in perspective, when the last ice sheets were retreating from North America and human civilization was just beginning to form its first settlements, many of the magnetars we observe today were in the throes of their most violent and energetic phase. Their magnetic fields are simply too powerful to be sustainable. The immense energy stored within them is constantly looking for a way to dissipate, and it does so through the very processes we've been discussing. The slow, steady glow of X-rays from accelerated particles and the catastrophic, sudden releases of starquakes and giant flares. Each of these events acts as a pressure valve, bleeding energy out of the system and causing the overall magnetic field to gradually, but inevitably, decay. Over a span of 10,000 to 100,000 years, this relentless loss of energy transforms the star. The magnetic field weakens by orders of magnitude, dropping from that staggering quadrillion Gauss down to the level of a more typical neutron star, which, to be clear, is still around 1 trillion Gauss and absolutely formidable. As the field decays, the star's behavior changes dramatically. The crust, no longer subjected to such unimaginable stress, stabilizes and ceases to fracture. The giant flares become a thing of the past, and the persistent X-ray glow that once made it shine so brightly in high-energy telescopes fades to a dimmer, quieter state. The magnetar, in effect, goes into retirement. It doesn't die, it simply settles down, often transitioning into a more conventional radio pulsar, spinning steadily and beaming its radio waves across the galaxy with a predictable rhythm. This life cycle gives us a fascinating narrative arc for these cosmic monsters. They are not eternal. They are a brilliant, explosive, and short-lived stage in the long, long life of a neutron star, a fleeting burst of extreme physics that, for a few tens of millennia, makes them some of the most spectacular and dangerous objects in the entire universe. Now we move from the star's explosive behavior to its very structure, where the magnetic field doesn't just influence the environment, it completely defines it. On a magnetar, the idea of a normal atmosphere is utterly impossible. The gravitational pull is so intense that any gas would be instantly crushed into the solid surface, yet we know these objects have an atmosphere of sorts. The resolution to this paradox is the magnetic field itself. It is so overwhelmingly powerful that it becomes the primary force organizing matter, creating what scientists call a magnetic atmosphere. This is an environment so alien that the very atoms within it are warped beyond recognition. In our world, an atom is a roughly spherical cloud of electrons orbiting a nucleus. But under the influence of a magnetar's field, that familiar shape is shredded. The field exerts such an immense pull on the negatively charged electrons that it stretches the entire atom into an bizarre, ultra-thin cylinder, a needle-like structure that can be hundreds of times longer than it is wide. Matter itself is forced into a form that would be unrecognizable anywhere else in the universe. This distorted atomic soup is then managed by the field in another extraordinary way. The magnetic field lines, arcing high above the star's surface, act like an invisible cage, capable of trapping a seething, hot blanket of ionized gas, a plasma. This isn't a gentle haze, it's a trapped, raging storm of particles. In some regions, this plasma can become so dense that it completely changes how the star radiates its energy. It can form a solid crust of plasma itself, a shell harder than diamond, under which the even more bizarre interior is hidden. This entire system creates a unique observational signature. The light emitted from this magnetic atmosphere is polarized, meaning its waves are forced to vibrate in a specific direction dictated by the magnetic field lines. By analyzing this polarized light with telescopes, astronomers can literally map the topology of the magnetic field from tens of thousands of light years away, reading the twists and turns of these invisible lines as if they were ink on a page. The magnetar's atmosphere, therefore, is not made of air. It is a construction of pure force, a prison of plasma and stretched atoms that serves as the ultimate laboratory for seeing how matter behaves when the fundamental rules of chemistry and physics are rewritten by magnetic dominance. But if you thought the sheer power of these magnetic fields was the final frontier, prepare to be amazed by the incredible methods we use to measure them. Pinpointing the exact strength of a magnetic field from 50,000 light-years away seems like an impossible task, yet astrophysicists have developed a remarkably precise tool for doing just that. The current record holder for the strongest magnetic field ever directly measured is a magnetar known as GROJ 1008-57, with a field strength of approximately 1 billion Tesla. To put that almost meaningless number into perspective, that is 10 raised to the 16th power Gauss, a value that pushes the very limits of what we believe is physically possible in our universe. So how do we know this? We certainly can't send a probe with a compass. The answer lies in decoding the very light the magnetar emits, specifically by looking for a tiny, telltale dip in its X-ray spectrum known as a cyclotron resonance scattering line. This phenomenon is a direct result of quantum mechanics playing out on a cosmic scale. As X-rays radiate from the star's surface, they pass through its trapped atmosphere of hot, magnetized plasma. In this intense magnetic environment, electrons are forced to orbit the magnetic field lines, and they can only exist at specific, quantized energy levels. It's like they're trapped on the rungs of a ladder and cannot exist between them. When an X-ray photon with the exact energy needed to bump an electron up to the next rung passes by, the electron absorbs it. This absorption creates a distinct dip or line in the otherwise smooth spectrum of X-rays we observe. The incredible part is that the energy of this absorption line is directly proportional to the strength of the magnetic field. It acts as a precise magnetic barometer. By meticulously measuring the energy of this cyclotron line with space telescopes like New Star, astronomers can perform the calculation and arrive at that staggering number of 1 billion Tesla. It's a flawless fingerprint left by the fundamental laws of physics that allows us to reach across the galaxy and quantify a force so powerful it defies earthly analogy. But the story of light near these cosmic powerhouses gets even stranger, forcing us to consider an effect so profound it could isolate a magnetar from the rest of the universe in a very real way. We've seen how the magnetic field warps matter. Now, we must understand how it warps the very light that tries to escape it. This brings us to a principle first discovered right here on Earth in 1845 by scientist Michael Faraday. He found that when a beam of polarized light, that is, light whose waves are all vibrating in a single, specific plane, passes through a transparent medium that's sitting in a magnetic field, something remarkable happens. The magnetic field causes the plane of that light's polarization to slowly rotate, like a needle on a dial being gently turned. We call this Faraday rotation, and it's a fundamental interaction between light and magnetism. On Earth, the effect is subtle, requiring sensitive instruments to detect. The magnetic fields we can generate are weak, and the media the light passes through, like certain types of glass, are not very dense. But this is a physical process that scales directly with the strength of the magnetic field and the density of the material the light is moving through. And that simple scaling is what transforms it from a laboratory curiosity into a universe-altering force in the vicinity of a magnetar. Now picture the environment around one of these stars. It's not a vacuum. It's filled with that trapped, seething plasma of ionized particles we described earlier, a super-dense, magnetized fog. Any photon of light generated at the magnetar's surface must fight its way through this incredibly hostile environment to escape into interstellar space. As it does, it encounters the full, unimaginable strength of the magnetic field permeating every cubic centimeter of that plasma. Under these conditions, Faraday rotation doesn't just nudge the polarization plane, it sends it into a frantic, uncontrollable spin. The effect would be so extreme and so rapid that it would completely and utterly scramble the information contained within the light signal. The orderly, polarized light that began its journey would emerge on the other side as an indecipherable mess, its original polarization state randomized beyond all recognition. This isn't a minor inconvenience, it represents a fundamental communications barrier. Imagine we were ever advanced enough to send a probe anywhere near such an object. Any attempt to send a signal back to Earth using any form of electromagnetic radiation, whether it's radio waves, visible light, or X-rays, would be futile. The data would be garbled by the magnetic field long before it could travel even a short distance away from the star. The magnetar, in effect, would be surrounded by a permanent, natural jamming field, a cloak of magnetic interference so perfect that it seals the object off from any meaningful remote investigation. It's a stunning thought that the very force that makes these objects so visible to us in high-energy light would also act as a shield, obscuring their deepest secrets from any technique that relies on reading the polarization of the light they emit. This single physical effect, gentle on Earth, becomes yet another example of how magnetars operate in a realm of physics where the ordinary rules are not just broken, but rewritten entirely. Now, this brings us to a question that often lurks in the back of our minds when we learn about such terrifying cosmic power. Could a magnetar actually threaten Earth? It's a premise worthy of a science fiction disaster movie, but the reality is both reassuring and humbling. Let's start with the most important fact: we are perfectly safe. The closest known magnetars are situated many thousands of light years away from our solar system. At such immense distances, even the most powerful giant flare would be nothing more than a fascinating light show for our telescopes, its dangerous radiation hopelessly diluted across the vast emptiness of interstellar space. Our planet's atmosphere and magnetic field provide more than enough protection from these distant, albeit spectacular, events. But to truly appreciate our safety, it's helpful to explore the nightmare scenario. Let's play with a terrifying what-if. Imagine a magnetar were not thousands, but merely 10 light-years away from us, cosmically speaking, right in our backyard. For context, the closest known star system to our own, Alpha Centauri, is just over 4 light-years away, so this hypothetical magnetar would be one of our very nearest stellar neighbors. Now, imagine this neighbor has a very bad day and unleashes a full-blown giant flare directly in our direction. The initial flash of gamma rays and X-rays would arrive at our planet just 10 years after the eruption, traveling at the speed of light. There would be no warning. The consequences would be swift and devastating. This wave of high-energy radiation would not just compress our ionosphere as the 2004 event did, it would violently rip through it. The primary victim would be our planet's ozone layer, that crucial shield in the stratosphere that protects all life on Earth from the sun's harmful ultraviolet radiation. The gamma rays would break apart the molecular bonds of ozone, O3, converting it back into ordinary oxygen, O2, in a catastrophic chemical reaction. In a matter of days, a significant portion of our global ozone layer could be obliterated. With that protective blanket gone, the surface of our planet would be bathed in lethal levels of ultraviolet radiation from our own sun. The effects on the biosphere would be apocalyptic. Ecosystems would collapse as phytoplankton in the oceans, the base of the marine food web, are decimated. Crop failures would be widespread on land. Rates of cancer and severe sunburn in animals, including humans, would skyrocket. It would likely trigger a mass extinction event on a scale not seen since the asteroid impact that ended the reign of the dinosaurs 66 million years ago. The chilling truth is that a magnetar doesn't need to vaporize our world to end life as we know it. It simply needs to remove our sunscreen from 10 light-years away. Thankfully, this is a horror story that exists only in theory. A thorough census of our cosmic neighborhood confirms that no such object lies within 10, 100, or even 1,000 light-years of Earth. The magnetars we know of are all at a safe and comfortable distance, allowing us to study their incredible power from the safety of our front row seat. This hypothetical exercise isn't meant to inspire fear, but rather to instill a profound respect for the forces at play in our universe and a deep appreciation for the fortunate cosmic isolation that allows our fragile world to thrive. Beyond just warping atoms and shredding light, these cosmic powerhouses serve another, equally vital role. They are nature's ultimate particle accelerators. Here on Earth, we construct monumental machines like the Large Hadron Collider, a 27-kilometer ring buried beneath the French-Swiss border, to smash particles together at breathtaking speeds, hoping to catch a glimpse of the fundamental laws that govern our universe. It is an incredible feat of human engineering, capable of accelerating protons to 99.999991% of the speed of light. But as powerful as it is, it pales in comparison to the raw, natural power of a magnetar. These stellar remnants are essentially colossal, natural versions of our particle accelerators, but operating on a scale and at energy levels we could never hope to achieve in a laboratory. They provide a unique window into high-energy physics, allowing us to observe the behavior of matter and energy under the most extreme conditions the universe has to offer. The process is a beautiful, if violent, demonstration of fundamental electromagnetism. The magnetar's surface is constantly boiling off a soup of charged particles, primarily electrons and protons. In a normal environment, these particles would simply drift away. But in the grip of a quadrillion Gauss magnetic field, they have no such freedom. They become trapped, forced to spiral along the incredibly strong magnetic field lines that arc away from the star's magnetic poles. As these particles are whipped along these invisible paths, they gain tremendous kinetic energy, much like a bead on a wire that's being shaken faster and faster. This acceleration is so efficient and so relentless that it can propel these particles to velocities indistinguishable from the speed of light itself. The energies involved are staggering, reaching levels trillions of times higher than those produced in any human-made collider. And when these ultra-relativistic particles are eventually released or collide with other matter, they scream out their energy across the electromagnetic spectrum, creating the persistent X-ray glow, and the explosive gamma ray flares that act as our primary beacon for finding these objects. This natural acceleration process creates a living laboratory for physics we can only theorize about. By analyzing the light and radiation from these events, astrophysicists can test the limits of the standard model of particle physics. They can search for signs of exotic particles or unusual interactions that might only occur at these energy frontiers. The magnetar's environment might even allow us to probe the quantum effects of incredibly strong magnetic fields, a realm where the equations of quantum electrodynamics are pushed to their absolute breaking point. Every burst of radiation, every flicker of X-ray light, is a data point sent to us from a natural experiment of unimaginable power. It's as if the universe provided us with the ultimate physics machine, and our job is simply to point our telescopes in the right direction and carefully decode the messages it sends. But the influence of these magnetic fields extends far beyond just particles and light. It reaches into the very fabric of the cosmos, warping the stage upon which the universe plays out. This brings us to one of the most mind-bending consequences of such immense power, a concept that sounds like it's pulled straight from theoretical fiction. We are all familiar with the idea of gravity, the attractive force described by Einstein's theory of general relativity, which tells us that mass and energy curve the fabric of space-time, creating what we perceive as a gravitational pull. A planet's mass creates a well in space-time, and objects roll down into that well. But what if something could create a hill instead? This is where the incredible energy density of a magnetar's magnetic field comes into play. A magnetic field is not nothing. It is a physical entity that contains an enormous amount of energy. general relativity tells us that all forms of energy contribute to the curvature of space-time, not just mass. In most cases, like with a star or a planet, the mass dominates this effect and the energy contribution is negligible. But on a magnetar, the energy stored in its magnetic field is so incomprehensibly vast that it becomes a primary contributor to the warping of space-time around the star. This leads to a phenomenon that can only be described as magnetic curvature. Now, the geometry of this curvature is where things get truly strange. The energy density of a magnetic field is not uniform in all directions. It creates a kind of pressure that is directed perpendicular to the field lines and a tension along them. When you translate this complex stress into the language of general relativity, the result is a type of spatial distortion that is fundamentally different from the curvature caused by a simple mass. In certain directions, particularly along the magnetic axis, this curvature can actually become repulsive. It would create a sort of hill in the fabric of space-time, causing objects or even light to experience a push away from the source rather than a pull toward it. On a quantum scale, for virtual particles popping in and out of existence in the magnetar's vicinity, this effect could manifest as a force that counteracts the star's immense gravitational pull in that specific direction. It wouldn't negate gravity entirely. The star's mass is still enormous, but it would create a bizarre and lopsided gravitational landscape. In one direction, you have the deep well of the star's mass pulling everything inward. In another, you have this magnetic hill pushing outward. This creates an environment where the effective gravity you would feel depends not just on where you are, but also on which way you are facing. It is a literal anti-gravity effect, not in the sense of science fiction force fields, but as a legitimate, repulsive component of gravity generated purely by the immense energy of a magnetic field. It is a stunning demonstration that gravity is not a simple monster. It is a complex beast whose nature is dictated by all forms of energy, and in the extreme laboratory of a magnetar, we can see its most exotic and counterintuitive forms come to life. And just as the ground shakes during an earthquake on our planet, sending out seismic waves that geologists use to understand Earth's interior, these distant starquakes send their own unique tremors through the fabric of the neutron star, creating signals that are a treasure trove of information for astronomers. When the magnetar's impossibly hard crust fractures, it doesn't just crack silently. The entire structure of the star begins to vibrate or ring like a colossal cosmic bell. These vibrations ripple through the star's interior and across its surface, modulating the intense X-ray glow that is constantly being generated by the magnetic field. This creates a very specific and fascinating pattern in the X-ray light we detect. The signal begins to oscillate, rising and falling in brightness with precise, rapid frequencies. These are known as quasi-periodic oscillations, or QPOS for short. They are the distinct sonic fingerprint of a starquake, a literal tremor in the data stream that signals a catastrophic geological event on an object light years away. The true power of detecting these oscillations lies in what they can reveal. Much like a bellmaker can tell a lot about the shape, size, and material of a bell by the specific note it produces when struck, astrophysicists can analyze the frequencies of these stellar rings to learn astonishing details about the neutron star's internal composition. This entire field of study is known as magnetar seismology, and it is our only direct window into the heart of these enigmatic objects. The different frequencies detected correspond to different types of waves traveling through the star's interior. Some might be shear waves moving through the solid crust, while others could be pressure waves diving deep into the bizarre nuclear superfluid of the core. Each type of wave is sensitive to different properties: the density of the crust, the stiffness of the core, the strength of the magnetic field permeating it all. By creating complex computer models and matching the observed QPO frequencies to the predicted vibrations of a neutron star, scientists can perform a remote diagnosis. It allows them to estimate the star's mass and radius with unprecedented precision, placing critical constraints on the elusive equation of state of ultra-dense matter, essentially helping us understand how matter behaves when it is crushed into forms that cannot possibly be recreated in any laboratory on Earth. Every starquake, as violent and destructive as it is, provides a fleeting glimpse into the most inaccessible places in the universe, turning the magnetar itself into a partner in its own discovery, ringing across the light years to tell us its deepest secrets. Perhaps one of the most thrilling developments in modern astronomy is how these local cosmic monsters might hold the key to unlocking a mystery that has captivated scientists for over a decade: the enigma of fast radio bursts. These events, known as FRBs, are among the most perplexing phenomena we've ever detected. For a few thousandths of a second, a source somewhere in the distant universe unleashes a blistering burst of radio waves that contains more energy than our sun emits over several days. The first one was discovered in 2007, buried in archival data from a radio telescope, and for years they remained a complete cosmic puzzle. Were they signals from alien civilizations, collisions between exotic stars? The theories were as wild as the bursts themselves. The mystery only deepened when astronomers realized some of these bursts were repeating, coming from the same location in the sky again and again, ruling out one-time catastrophic events like a star blowing itself apart. We knew they were powerful, we knew they were far away, and we had absolutely no idea what was causing them. Then, in April 2020, a breakthrough occurred that forever changed the conversation. A magnetar within our own Milky Way galaxy, officially named SGR 1935+21-5, had an exceptionally hyperactive day. It erupted in a storm of X-ray and gamma-ray bursts, which was interesting but not entirely unusual for such a volatile object. But this time, radio telescopes were watching closely. The researchers operating the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, telescope, along with the Survey for Transient Astronomical Radio Emission 2, or STARE-2, in the United States, detected something unprecedented. Coming from the exact same location and at the exact same time as the magnetar's high-energy tantrum was a tremendously powerful burst of radio waves. It wasn't coming from a distant galaxy, it was right here in our cosmic backyard, and it perfectly matched the profile of a so-called extragalactic FRB. This was the smoking gun the astronomy community had been searching for. This single observation provided overwhelming evidence that, at the very least, one class of FRBs is produced by magnetars. The theory fits together beautifully. We already knew magnetars were capable of producing hyperflares of energy across the electromagnetic spectrum. A giant flare's initial spike of gamma rays is often followed by a longer-lasting radio afterglow. The thinking is that the same catastrophic event, a starquake or a magnetic reconnection, that produces the initial flash also creates a rapidly expanding fireball of plasma. This shockwave then plows through the magnetar's own intense magnetic field and the cloud of material surrounding the star, and in doing so, it generates a coherent lighthouse-like beam of radio waves. This model elegantly explains the incredible energy and the fleeting duration of the bursts. Of course, the universe is rarely so simple as to have just one answer. While the galactic FRB confirmed magnetars as a source, it's highly likely they are not the only source. The incredible diversity of FRBs we detect, some are one-off events, some repeat erratically, and some have incredibly complex structures in their signals, suggests that multiple cosmic engines might be at work. Some bursts could still be from merging neutron stars or other exotic phenomena, but the magnetar connection has given scientists a solid, observable foundation to build upon. It has transformed FRBs from a total mystery into a powerful new tool for astronomy. Because these radio waves travel for millions or even billions of years to reach us, they carry with them a unique imprint. They sweep through the tenuous gas between galaxies, and this interaction leaves a telltale sign on the signal, allowing astronomers to measure the amount of material the burst has traveled through. This turns each FRB into a cosmic probe, helping us map the otherwise invisible distribution of matter in the vast cosmic web. The same terrifying magnetic fury that could shred a planet from light years away is now helping us piece together the large-scale structure of the entire universe. Approaching one of these cosmic monsters would be an experience that defies all human intuition, a journey into a realm where physics as we know it ceases to apply. From 1,000 kilometers away, a distance where our own planet would still feel vast and the star itself would be a tiny, brilliant point of light, the true effects would begin to manifest in ways that are both invisible and utterly catastrophic. Your first instinct might be to worry about the immense gravitational pull, and rightly so. The gravity on the surface of this 12-mile-wide sphere is 100 billion times stronger than Earth. But long before you could even get close enough for that pull to become the primary concern, the magnetic field would have already performed its gruesome work. The force wouldn't feel like a simple push or pull. There would be no violent shaking or crushing pressure in the conventional sense. Instead, the effect would be subtler, far more precise, and infinitely more strange. The magnetic field is so powerful that it would begin to interact directly with the very atoms that constitute your body. In our world, atoms are mostly empty space, with electrons buzzing in a cloud around a dense nucleus, and they are generally unaffected by magnetic fields. But here, the field is so strong it overwhelms the electromagnetic forces that usually hold atoms in their familiar spherical shapes. This is where a concept known as the van der Waals force comes into play, a weak intermolecular force we experience every day. It's the reason geckos can climb walls and why water molecules stick together. But under the influence of a magnetar's field, this faint force is amplified to an astronomical and lethal degree. The field would violently polarize your atoms, stretching the electron clouds into incredibly long, thin, needle-like shapes, all aligned with the magnetic field lines. The van der Waals forces between these newly shaped, polarized atoms would become immensely powerful, effectively trying to glue all these atomic needles together. Your body's molecules would be forcefully reconfigured, pulled into alignment like iron filings near a bar magnet, but with consequences that are horrifically biological. The complex, delicate structures of your cells and tissues, which rely on specific molecular shapes to function, would be violently distorted. Proteins would unravel, cell membranes would fuse together, and DNA would be shredded. You wouldn't be torn apart by a blunt force. You would be meticulously disassembled, molecule by molecule, into a stream of polarized matter, your physical form reorganized into a structure that more closely resembles a crystalline, one-dimensional filament than a human being. It is a fate that makes being spaghettified by a black hole seem almost straightforward, a reminder that in the cosmos there are forces far more bizarre and terrifying than gravity alone. Within the chaotic heart of a magnetar, where matter is crushed into forms beyond our imagination, lies a bizarre state of physics that helps explain how such immense magnetic power can persist for millennia. It all comes down to the concepts of superconductivity and superfluidity, phenomena we can observe in labs on Earth but which operate here on a truly cosmic scale. Deep inside the neutron star, the pressure is so unimaginably high that atomic nuclei can no longer maintain their structure. They dissolve into a sea of their constituent parts, a quantum soup of neutrons and protons swimming in a broth of electrons. Under these extreme conditions, something extraordinary happens. This nuclear material is thought to transition into a superfluid and a superconductor. A superfluid is a liquid that can flow without any friction whatsoever, and a superconductor is a material that can carry an electrical current with absolutely zero resistance. In the core of a neutron star, it's theorized that the neutrons become a superfluid, while the protons form a superconducting state. This superconducting proton sea is the key to understanding the longevity of a magnetar's magnetic field. In a normal material, any electrical current and therefore any magnetic field it generates will naturally decay over time due to electrical resistance, which dissipates energy as heat. Think of it like a flywheel spinning in air. Friction will eventually bring it to a stop, but in a superconductor there is no resistance. An electrical current, once started, can theoretically flow forever without losing any energy. It's like that same flywheel spinning in a perfect vacuum. With nothing to slow it down, it just keeps going. Inside the magnetar, the immensely powerful electrical currents that generate the magnetic field are not running through ordinary copper wire. They are flowing through this frictionless sea of superconducting protons. This allows the currents to persist for astronomical timescales, effectively trapping the magnetic energy within the star and preventing it from simply dissipating away. It acts as a perfect cosmic battery, locking in that phenomenal magnetic strength for tens of thousands of years. But the role of this quantum soup doesn't stop there. The superfluid neutrons play their own critical part in the star's dramatic behavior. Because they have no viscosity, they can spin independently of the star's solid crust. This difference in rotation between the frictionless interior and the rigid outer shell creates immense stresses which can wind up the internal magnetic fields even further, adding energy to the system and potentially triggering the starquakes and eruptions we observe from Earth. The superfluid interior essentially acts as a vast reservoir of energy and a driver of instability, ensuring that the magnetar remains a violently active object throughout its relatively short, spectacular lifetime. This intricate dance between a superfluid core and a superconducting proton sea provides the microphysical engine that sustains the macrocosmic fury, turning the magnetar's interior into the most extreme and fascinating laboratory for quantum mechanics in the known universe. But if you think the sheer strength of these fields is impressive, wait until you grasp their complexity. We've been talking about these magnetic fields as if they are simple, smooth loops of force, like the perfect arcs you see around a bar magnet in a textbook diagram. The reality is far more chaotic and infinitely more fascinating. Inside a magnetar, the magnetic field is not a static, well-behaved structure. It is a living, writhing, and violently tangled knot of energy. The very processes that created the incredibly rapid spin of the newborn star and the turbulent churning of its superfluid interior guarantee that this field will be anything but simple. It gets wound up, twisted, and contorted, much like someone relentlessly twisting a rubber band tighter and tighter. This creates immense kinks and tangles in the magnetic field lines, storing absolutely colossal amounts of stress and strain. You can think of it as a cosmic version of a knotted-up garden hose. When the water is turned on at low pressure, the hose might just writhe a bit, the knots holding their ground. But if you were to crank the pressure up to an astronomical level, those knots would store a huge amount of pent-up energy, threatening to burst or suddenly release with explosive force. In a magnetar, the internal pressure from the star's spin and dynamics is constantly trying to force the magnetic field into an even more twisted state. The field lines are pinned at their bases in the star's crust, but their tops are free to move in the magnetosphere above. This difference allows them to be wound up like a spring, storing mind-boggling amounts of energy in the process. These twisted configurations are not stable. They are metastable, existing in a precarious state of balance that can be shattered by the slightest disturbance. And this is where the true cosmic fireworks begin. This knotted, stressed magnetic topology is the most likely trigger for the giant flares and catastrophic energy bursts we observe. The system can only hold its distorted shape for so long. Eventually, the stress becomes too great, and the field must find a way to reorganize itself into a simpler, lower energy state. The kinks and twists in the field lines suddenly snap and reconnect in a process called magnetic reconnection. It's as if that over-twisted rubber band finally breaks, or that knotted garden hose suddenly untangles itself all at once, releasing every bit of stored energy in a single, violent instant. This sudden unwinding converts the immense stored magnetic energy directly into thermal energy and radiation, catapulting superheated plasma to relativistic speeds and generating that blinding flash of gamma rays and X-rays that can outshine entire galaxies. The topology of the field, its twisted, complex shape, isn't just a curiosity. It is the very mechanism that loads the cosmic gun, storing the energy until the moment it is finally, catastrophically fired. While we've been focused on the magnetars within our own cosmic neighborhood, the Milky Way, the hunt for these extreme objects extends far beyond our galactic borders. Searching for magnetars in other galaxies is one of the most formidable challenges in modern astronomy, a true testament to both the limitations of our technology and the sheer scale of the universe. The primary obstacle is, of course, distance. The closest known magnetar to Earth is still thousands of light years away, but it's within our own galaxy. To find one in another galaxy means looking for a single, faint, flickering point of light millions of light years away. It's like trying to spot a specific lighthouse from a ship at sea during a storm, only that lighthouse is in an entirely different ocean on the other side of the planet. The incredible energy of a magnetar's outburst helps, as a giant flare can briefly outshine its entire host galaxy in high-energy light. But that flash is over in less than a second, making catching it a matter of incredible luck and precise timing. Despite these immense challenges, astronomers have had some remarkable successes. The most notable discoveries have come from our nearest galactic neighbors, the dwarf satellite galaxies that orbit the Milky Way. The most famous of these is the detection of a magnetar in the Large Magellanic Cloud, a galaxy about 160,000 light-years away. This object was identified not by its persistent X-ray glow, which would be too faint to pick out individually at that distance, but by catching it in the act of eruption. When it unleashed a giant flare, space-based observatories trained on that region of the sky were able to triangulate the source of the immense energy burst and confirm its extragalactic origin. This was a monumental achievement, proving that magnetars are not a unique feature of our own galaxy, but a universal phenomenon. The motivation for this painstaking search goes far beyond simply adding another pin to the cosmic map. By finding magnetars in other galaxies, astronomers can begin to answer fundamental questions about the population and behavior of these objects across the cosmos. Is the number of magnetars we see in the Milky Way typical? Does their formation depend on the specific environment or metallicity, the abundance of elements heavier than hydrogen and helium of their host galaxy? By comparing the populations in different types of galaxies, from small, metal-poor dwarf galaxies to large, metal-rich spirals, we can start to understand the recipe needed to create such a monstrous object. If we find that certain types of galaxies have more or fewer magnetars, it tells us something crucial about the life cycles of the most massive stars and the conditions required for that internal dynamo to wind up to magnetar levels. Each extragalactic magnetar discovered is a critical data point, helping us move from studying individual cosmic curiosities to understanding them as a class of objects that play a role in the grand evolutionary story of galaxies themselves. This historical distinction in naming actually reveals a fascinating chapter in the story of their discovery and how our understanding of these objects evolved over time. For a period, astronomers were essentially observing the same type of cosmic beast, but through two different sets of behaviors, leading them to believe they might be dealing with two separate species. The objects we now call soft gamma repeaters were first detected in the late 1970s by specialized satellites designed to monitor for nuclear weapons tests. These instruments kept picking up brief, intense bursts of gamma rays that weren't coming from Earth but from deep space, The key characteristic that set them apart was right there in the name. They repeated. Unlike a supernova, which is a one-time cataclysm, these sources would flare up again and again from the same patch of sky. The soft descriptor refers to the specific energy of the gamma rays they emitted, which were slightly lower in energy compared to other cosmic explosions. On the other side of the coin, there were the anomalous X-ray pulsars, or XPS. These objects were identified by their persistent, powerful glow in X-rays and their steady, pulsing rhythm, much like the radio pulsars we're more familiar with. However, their energy output was far too high to be explained by the standard model of a spinning neutron star slowly losing its rotational energy. They were anomalous because their power source was a complete mystery. For years, the debate continued. Were soft gamma repeaters and anomalous X-ray pulsars related, or were they entirely different classes of stellar remnant? The turning point came as observations accumulated and technology improved. Astronomers began to notice that some anomalous X-ray pulsars would occasionally, quite unexpectedly, emit the same kind of soft gamma-ray bursts that defined the SGRS. Conversely, when a soft gamma repeater was quiet between its explosive outbursts, it looked for all the world like an anomalous X-ray pulsar, glowing intensely in X-rays and often exhibiting a steady pulse. The evidence became undeniable. These were not two different families of objects, they were one and the same. The entire diverse behavior, the steady X-ray glow, the periodic pulsing, and the catastrophic gamma-ray bursts could all be powered by a single, unimaginably powerful engine, an immense decaying magnetic field. The name magnetar was proposed as the unifying theory that explained every facet of their behavior, and it stuck. Today, we understand that whether an object is historically labeled an SGR or an XP simply depends on which of its dramatic personalities we happen to observe first. It's a perfect example of how science revises its classifications as new data comes to light, weaving separate threads of evidence into a single, breathtaking tapestry. Now we turn to a more subtle but equally profound effect of these incredible magnetic fields, one that plays out over millions of years, their influence on how a neutron star cools. From the moment of its birth in a supernova, a neutron star is unimaginably hot, with internal temperatures reaching hundreds of billions of degrees. But it is a cinder slowly fading in the dark, destined to cool over eons. For a typical neutron star, this cooling process is governed by two main mechanisms: the slow leakage of heat from its surface as photons of light, and far more importantly, the rapid emission of elusive particles called neutrinos from its super-dense core. These neutrinos, which barely interact with matter, can carry away immense amounts of thermal energy directly through the star and out into space, acting as a supremely efficient cooling system. This process is dictated by the laws of physics governing matter at nuclear densities. But a magnetar is not a typical neutron star. Its monstrous magnetic field doesn't just affect its explosive surface activity. It reaches deep into the star's interior, altering these fundamental cooling processes in two key ways. First, it can directly impact neutrino production. The dominant theory suggests that the incredibly strong field can modify the weak nuclear interactions happening in the core, the very processes that create neutrinos. It's as if the magnetic field itself becomes a participant in these subatomic reactions, potentially enhancing or suppressing the rate at which neutrinos are born, thereby speeding up or slowing down the core's ability to shed its ferocious heat. Second, the field dramatically alters the thermal properties of the star's crust. Heat from the interior must conduct through this solid, ultra-dense shell before it can be radiated from the surface. In a normal neutron star, this heat flows along a temperature gradient. However, a magnetar's crust is not a uniform material. It is a crystalline structure ruthlessly organized by the magnetic field. The field lines create a preferred direction for everything, including heat flow. Thermal conductivity becomes highly anisotropic, meaning heat travels much more easily along the direction of the magnetic field lines than across them. Imagine the crust not as a simple slab of material, but as a vast collection of incredibly efficient thermal pipes all running in the same direction, defined by the magnetic field's geometry. If the field is aligned favorably, heat can be channeled efficiently to the surface. If it's not, the heat can become trapped, effectively insulating the hot interior and slowing the overall cooling rate. This means two magnetars born at the same time with the same mass could, millions of years later, have vastly different surface temperatures simply because of the orientation and strength of their magnetic fields. It's a remarkable thought that this invisible architecture of force can govern the long-term thermal evolution of a stellar corpse, leaving a lasting imprint on its temperature eons after its brilliant, violent youth has faded. But if the sheer violence of the environment weren't enough to deter any potential planet, the magnetic field itself presents a final, insurmountable obstacle to life. A planet orbiting within the magnetar's sphere of influence would find its own magnetic personality completely and utterly dominated. On Earth, our planetary magnetic field is a protective shield, deflecting the solar wind and carving out a safe pocket of space called the magnetosphere. But in the grip of a magnetar, this protective bubble would be violently compressed and warped beyond all recognition. The external pressure from the magnetar's field would be so immense that it would crush the planet's own magnetosphere down to a thin, ineffective shell, leaving the surface fully exposed to the relentless barrage of high-energy particles. This would not only strip away any lingering atmosphere, but also bathe the entire world in a continuous, lethal shower of radiation, ensuring that even the hardiest extremophile microbes could never gain a foothold. The very force that makes life possible on our world would be rendered useless, overwhelmed by a power that redefines the word extreme. And if you thought visualizing these distant titans was a challenge, wait until you hear one. While the cold vacuum of space carries no sound, we humans have found a profoundly moving way to bridge that sensory gap, transforming raw data into an experience that resonates on a deeply primal level. It's a process called datassonification, and it allows us to give these silent, spinning monsters a voice. By taking the precise, rhythmic X-ray pulses emitted by a magnetar like SGR 180620, and converting their frequency and intensity into sound waves within the range of human hearing, we can listen to the heartbeat of a stellar corpse. The result is not a musical melody, but something far more haunting and mechanical. It manifests as an eerie, rhythmic clicking, a persistent and steady ticking that echoes the star's incredible rotation. Each click represents a lighthouse beam of intense radiation sweeping past our line of sight, a direct auditory signal of a cosmic clock keeping perfect time. But this voice is not static. It tells a story of deceleration and decay. As the magnetar's immense magnetic field acts as a brake, slowly sapping its rotational energy, the star's spin gradually slows down. This change is imperceptible to our eyes watching a light curve on a graph, but to our ears, it's a dramatic and unmistakable shift. In the sonified data, that steady, rapid-fire clicking begins to slow. The intervals between each click grow longer and more pronounced, the rhythm deepening and stretching out over time. That speeding down is the direct sound of energy loss, an acoustic representation of the magnetic field's overwhelming power, literally slowing the spin of a city-sized object with the mass of a sun. It transforms an abstract astrophysical concept into a tangible, auditory experience. We are not just learning about the star's spin down, we are hearing it age, we are listening to it lose energy, we are witnessing the relentless drag of its own magnetic fury translated into a soundscape. This ability to hear the cosmos adds an entirely new dimension to our understanding, creating an intimate and surprisingly emotional connection to an object that exists in a realm of physics far beyond our own. It reminds us that behind every data point on a screen, there is a real physical phenomenon, and sometimes giving it a voice is the most powerful way to comprehend its true nature. And yet, even with all these observable phenomena, we are only scratching the surface of the true weirdness. To grasp the full implications of a magnetar's power, we must venture into the realm of quantum electrodynamics, or QED, the theory that describes how light and matter interact. This is where the physics becomes truly mind-bending. According to QED, even the vacuum of space is not truly empty. It is a seething, bubbling quantum foam where pairs of virtual particles, a particle and its antiparticle, constantly pop into and out of existence for unimaginably short moments before annihilating each other. In our everyday world, and indeed across most of the universe, this bizarre quantum activity is completely undetectable. It's the background hum of reality that we never notice. But place that same vacuum within the influence of a magnetar's field, and everything changes. A magnetic field of this magnitude does not just influence particles, it fundamentally alters the very properties of the empty space itself. The theory of quantum electrodynamics makes a stunning prediction. In the presence of an ultra-strong magnetic field, the vacuum is expected to become birefringent. Birefringence is a property we usually associate with certain crystals like calcite, which can split a beam of light into two separate rays. This happens because the crystal has a different index of refraction for different polarizations of light, meaning light travels through it at slightly different speeds depending on the orientation of its wave. For the quantum vacuum near a magnetar, this effect is taken to an astronomical extreme. The incredibly strong magnetic field polarizes that sea of virtual particles, affecting how they interact with real photons of light passing through. This polarization causes the vacuum to behave like a giant cosmic crystal. A photon's speed, according to Einstein's theory of relativity, is always constant in a vacuum. But here, the vacuum itself is changed. Light of one polarization would effectively travel through this magnetized quantum foam at a slightly different speed than light of another polarization. It's a fantastically strange idea that nothingness itself can be twisted and manipulated to have a measurable structure, all by the sheer force of a magnetic field. This isn't just theoretical speculation, it's a potential observational target for the future. The effect would be tiny and incredibly difficult to detect, but magnetars provide the perfect laboratory. By studying the polarized X-rays that manage to escape from these objects, astronomers hope to one day find the telltale signature of this vacuum birefringence. It would be a monumental discovery, providing the first direct experimental evidence that empty space itself has properties that can be altered by immense forces, confirming a key prediction of quantum electrodynamics in a regime we can never hope to recreate on Earth. It would show us that the universe, even in its utter emptiness, is far more strange and wonderful than we ever imagined. Just when we thought we had the magnetar story neatly figured out, the universe, as it so often does, throws us a spectacular curveball. For years, the model was beautifully simple. Immense magnetic field strength equals violent magnetar-like activity. But then, astronomers began to find a few bizarre outliers that defied this logic, objects now known as low-field magnetars. These cosmic rebels are neutron stars that exhibit all the classic, dramatic hallmarks of a magnetar: the intense X-ray glow, the sudden starquakes, the explosive bursts, but with one deeply confusing detail. When their magnetic fields are measured, they turn out to be thousands of times weaker than the textbook quadrillion Gauss standard, placing them squarely in the range of ordinary pulsars. It's the equivalent of finding a tiny campfire that somehow produces the heat and light of an erupting volcano. The observed effect simply doesn't match the available fuel. This discovery sent a tremor through the astrophysics community, forcing a complete re-evaluation of what we thought we knew about the engine inside these stellar corpses. The existence of these low-field magnetars suggests that the visible external magnetic field we can measure from light years away might only be telling part of the story. The leading theory to explain this paradox points to a hidden powerhouse buried deep within the star's interior. Imagine a neutron star with a complex, layered magnetic history. It's possible that during its turbulent birth, the internal dynamo created a magnetic field that was incredibly twisted and tangled, with its strongest components buried deep in the superfluid, superconducting core. The field we see on the surface, the one we can measure, might just be the superficial tips of a much deeper, much more powerful magnetic iceberg. Over thousands of years, this internal field could be slowly rising up through the star's layers, like a bubble moving through molasses, transferring its energy and stressing the crust to trigger explosions, all while the surface field we observe remains deceptively calm. In this scenario, a low-field magnetar isn't a weakling at all. It's a sleeping giant whose true power is still mostly concealed, its bursting activity a hint of the ferocious energy churning just beneath the surface. Another compelling idea focuses on the incredible heat left over from the star's formation. A newborn neutron star is born scorching hot, and it can take millions of years to cool down. This residual thermal energy is absolutely vast. For a low-field magnetar, this internal heat might provide an alternative power source for its outburst. The intense heat could keep the star's solid crust more malleable and prone to fracture, while also driving powerful convection currents in its interior. These currents could, in turn, generate localized, strong magnetic spots or stir up existing magnetic fields, creating the stresses needed for a starquake or a burst without requiring a globally immense field. It's a fascinating possibility that a magnetar's volatility might not always be a pure symptom of magnetic strength, but could sometimes be a sign of its prolonged and feverish youth, a thermal engine taking over where the magnetic one has begun to fade. These strange objects are more than just cosmic anomalies. They are critical puzzles that force us to refine our models. They tell us that the pathway to a starquake or a giant flare might not be a one-lane road powered solely by magnetic decay. There could be multiple routes to the same explosive destination. The discovery of low-field magnetars has opened up an entirely new chapter in high-energy astrophysics, reminding us that for every rule we establish about the universe, there is almost always an exception waiting in the shadows, challenging our assumptions and pushing us toward a deeper, more nuanced understanding of these magnificent cosmic powerhouses. Looking far beyond their terrifying power, these cosmic monsters might just hold the key to a future we can scarcely imagine, one where humanity voyages between the stars. In such a grand endeavor, our current navigation systems would be utterly useless. The familiar constellations would be unrecognizable from another solar system, and the signals from Earth's GPS satellites would be far too weak to detect even at our closest stellar neighbors. Future interstellar travelers would need a universal galactic positioning system, a fixed network of reference points visible from anywhere in the Milky Way. Incredibly, magnetars, with their perfectly predictable and unique pulsations, are the only known objects in the cosmos that could possibly serve this purpose. Think of each magnetar as a natural lighthouse, but one whose beacon is not a simple flash of visible light, but a piercing, rhythmic pulse of X-rays. This is the key to their navigational potential. While all pulsars spin, a magnetar's spin is remarkably stable over the short term, and most importantly, each one has a completely unique rotational fingerprint. One magnetar might pulse exactly every 6 seconds, another every 8.2 seconds, and a third every 2.7 seconds. This period is its fundamental, unchanging identity, a cosmic IP address written in X-rays. A spacecraft equipped with a sensitive X-ray telescope could easily detect these pulses. By simply measuring the precise interval between the clicks of just 3 different magnetars, a navigational computer could perform a form of triangulation. Since the exact three-dimensional position and pulse period of each magnetar would be meticulously catalogued, the spacecraft could compare the observed pulse rates with the known catalog values. The tiny differences in the arrival times of the pulses, caused by the varying distances to each magnetar, would allow the ship's computer to calculate its own precise location within the galaxy, potentially down to a matter of kilometers, even from thousands of light years away. The advantages over using ordinary pulsars are significant. While radio pulsars have been proposed for a similar concept, their signals are weaker and can be scattered by the interstellar medium. A magnetar's X-ray pulse, by comparison, is a focused, high-energy drill bit that punches cleanly through cosmic dust and gas, providing a stronger, clearer signal over vast intergalactic distances. This isn't just science fiction, it's a concept with roots in real-world science. The plaques on the Pioneer probes and the golden records on the Voyager spacecraft included a pulsar map showing Earth's location relative to 14 nearby pulsars, a message to any potential finders on how to find our home solar system. We've already begun thinking of the galaxy in these terms. For a future civilization capable of crossing the light years, a network of magnetars would provide a fixed, reliable, and eternal grid on which to chart a course through the infinite dark, turning the most destructive forces in the universe into the very beacons that would guide us safely home. Yet for all we've learned, the study of these magnetic monsters is really just beginning, and the next decade promises to revolutionize our understanding in ways we can barely imagine, thanks to a new generation of astronomical observatories designed to see the universe in sharper detail than ever before. Leading this charge is the Advanced Telescope for High-Energy Astrophysics, or Athena, a mission being developed by the European Space Agency with a planned launch in the 2030s. This isn't just an incremental upgrade, it's a quantum leap in X-ray astronomy. Athena's colossal X-ray mirror will have a collecting area over 100 times larger than that of NASA's current flagship X-ray observatory, the Chandra X-ray Observatory. This immense light-gathering power, combined with revolutionary new detectors, will allow it to perform high-resolution spectroscopy on magnetars with a precision that borders on the magical. Imagine being able to not just detect the cyclotron lines that reveal a magnetic field's strength, but to map the intricate details of those lines as they shift and change during a starquake or a flare. Athena will be able to watch the magnetic field itself reconfigure in real time, tracing how energy propagates through the star's crust and magnetosphere. It will be like moving from a simple photograph of a storm to a high-resolution, slow-motion video that tracks every gust of wind and every drop of rain. This will allow scientists to finally test the complex models of magnetic field decay and crustal fracture with direct, unambiguous data, moving from informed speculation to concrete knowledge about the inner workings of these stellar power plants. On the other side of the electromagnetic spectrum, a colossal ear is being built on the ground to listen to the radio whispers of the cosmos. The Square Kilometre Array, or SKA, is not a single telescope but a vast network of thousands of radio antennae spread across South Africa and Australia. When its first phase is completed in the late 2020s, it will be the most sensitive radio telescope ever constructed, capable of detecting the faintest signals from the distant universe. For magnetar research, the SKA's power will be its unparalleled ability to perform rapid, wide-field monitoring of the entire sky. Its core mission will be to conduct vast, continuous surveys, meaning it will be watching constantly, patiently waiting for the universe to put on a show. This makes the SKA the perfect instrument for catching one of the holy grails of high-energy astrophysics, the very beginning of a magnetar giant flare. Current telescopes often only catch these events after they've already peaked, like arriving at the cinema after the movie has started. The SKA's relentless gaze means there's a very high probability it will be looking in the right place at the right time when a magnetar in our galaxy or a nearby neighbor decides to erupt. It could capture the initial milliseconds of the eruption, potentially detecting the elusive radio signal that is theorized to precede the colossal gamma-ray flash. This would be a monumental discovery, providing the definitive proof of the theoretical fireball model and revealing the exact sequence of events that triggers these universe-shattering explosions. Perhaps most excitingly, these telescopes won't work in isolation. The future of astronomy is multi-messenger, the practice of observing a single cosmic event across many different wavelengths of light, and even with other carriers of information like gravitational waves or neutrinos. A coordinated observing campaign might work like this. The SK detects the first faint radio chirp of a magnetar going active. Within milliseconds, an automated alert is sent to observatories around the world and in space. Athena swivels to focus its powerful X-ray eye on the target, while optical and infrared telescopes on mountaintops join the watch. If the event is powerful enough, instruments like the next-generation gravitational wave observatory, the Einstein telescope, might even strain to detect a literal vibration in spacetime caused by the Starquake. This synchronized effort would give us a complete, multifaceted movie of a magnetar's outburst, from its initial rumble to its final fading echo. It would allow us to understand how energy is partitioned, how much goes into seismic waves shaking the star, how much is blasted into space as radiation, and how much is used to accelerate particles to near light speed. This isn't just about satisfying scientific curiosity. It's about stress testing the laws of physics in the most extreme environment nature can provide. Each new observation is a data point that could help us refine our theories of quantum electrodynamics, nuclear matter, and gravitation itself. The next generation of telescopes are more than just bigger mirrors and more sensitive detectors. They are the keys to unlocking a new chapter in fundamental physics, written in the furious language of magnetars. And so we arrive at the final, almost philosophical chapter in the story of these cosmic powerhouses, a journey that stretches across timescales so vast they defy human comprehension. We've witnessed their violent births and their energetic, explosive youth, but every great fire, no matter how fierce, must one day burn out. The incredible magnetic fields that define a magnetar's existence are not eternal. They are a brilliant, fleeting flash in the cosmic dark, destined to fade over tens of thousands of years as they bleed their energy into space through flares and steady radiation. This decay is the star's slow march toward a quiet retirement, a transition from a volatile magnetar into a more sedate, ordinary neutron star. But even that state of relative calm is not the end of the story. It is merely the beginning of an unfathomably long and lonely final chapter that plays out over quadrillions of years. As the eons stretch on, the neutron star's rotation continues to slow, its relentless pulses becoming further and further apart until they finally cease altogether. The thermal glow from its surface, the last remnant of its fiery birth, will also gradually dim. The universe itself is changing around it. Stars throughout the cosmos will have long since exhausted their nuclear fuel, dying in a variety of ways, some fading to white dwarfs, others collapsing into black holes. New star formation will have ended, as the raw materials for building new suns are locked away in these stellar corpses or dispersed into an ever-cooling void. The era of stars will be over, and the cosmos will be plunged into a profound and deepening darkness, a future cosmologists call the degenerate era. In this unimaginably distant time, the universe will be a vastly empty and cold place dominated by these remnants. And among them, the neutron stars will be the ultimate survivors. Their incredible density makes them nearly indestructible. They will silently coast through the expanding darkness for time frames that make the current age of the universe seem like a single blink. But even these ultimate timekeepers are not completely immutable. According to some theories, over periods of time so long they are measured in googolls of years, a one followed by 100 zeros, the very protons and neutrons that make up the star's core may themselves begin to decay, a process predicted by some extensions of the standard model of particle physics. If this occurs, the ultra-dense matter of the neutron star will very slowly evaporate into radiation and lighter particles. This process would leave behind not a complex, spinning relic, but a perfect crystalline sphere of pure iron. All the heavier elements that were forged in the supernova and compressed during its birth would have broken down, leaving behind the most stable nucleus in the universe, iron 56. This cold, dark sphere would be the final, inert form of the star, a silent monument to a universe that once teemed with light and energy. It would drift through an almost perfect vacuum, a ghost of a ghost, in a cosmos that is expanding so rapidly that every other object has long since disappeared over the horizon of visibility. The once mighty magnetic field, capable of tearing apart atoms from 1,000 kilometers away, will have dissipated into nothingness eons prior, its incredible energy lost to the void. The frenetic activity, the starquakes, the gamma-ray flares, all of it is gone, silenced forever. The story that began with one of the most violent explosions in the universe concludes in the absolute quiet of the deep freeze. It is a humbling and poignant finale, a reminder that all things, even the most powerful forces in the cosmos, are subject to the relentless flow of time and the ultimate triumph of entropy. So we've traveled from the unimaginable violence of a stellar collapse, where a dying star's last breath forges a cosmic monster, to the serene, almost meditative ticking of its X-ray pulse, a rhythm that guides us toward the farthest reaches of future navigation. We've witnessed starquakes powerful enough to crack a city-sized sphere of material harder than diamond, and magnetic fields so intense they don't just bend light. They twist the very quantum vacuum of empty space into a cosmic crystal. These are not distant, abstract curiosities. They are active, violent, and breathtakingly precise natural laboratories, operating at energy extremes we could never hope to recreate on Earth. They push the very laws of physics to their breaking point, and in doing so, reveal deeper truths about matter, energy, and the fabric of reality itself. They are a testament to the fact that the universe's most powerful forces are often its most invisible, and its greatest wonders are hidden in plain sight, waiting only for us to learn how to look. The story of Magnetars is a humbling reminder of our place in the cosmos, not as passive observers, but as active participants in a grand, ongoing investigation. The universe is brimming with phenomena that challenge our understanding and ignite our curiosity. So what other magnetic mysteries do you think are waiting to be unraveled? Was there a fact that completely reshaped how you see the cosmos? Let us know your favorite moment from this journey in the comments below. And if you want to join us for more deep dives into the universe's greatest secrets, don't forget to like this video and subscribe to the channel.